happening is basically the top of a solar cell is the negative, and the bottom side of the cell, we can't see the back side of it, but the underside of this cell that's laid on here and laminated on there is the positive. So what they're doing is they're basically weaving this little tabbing wire, this little aluminum wire, like thread, up top to bottom, top to bottom. And what they're doing is connecting the positive to the negative to the positive, and what that does is that gives us 1.5 volts because each of these is 0.5 volts. So 0.5, 0.5, 0.5 together, we get 1.5 volts. So one interesting thing about silicon, a silicon cell, is that no matter how big or how small a piece of silicon is, it always carries a voltage of 0.5. So even the big panels on the roof, those big squares, those are still 0.5 volt. The difference is that the more surface area you have, the more amperage you can put through the silicon. So the amperage can be unlimited depending on how big the surface area is, but the voltage will always be 0.5. So really here we're looking at the very concepts to do all solar wiring. We have 3 cells wired together to give us the voltage that we want, in this case 1.5 volts, to run this little load. All they're doing on the roof of your school is taking solar cells, they wire the solar cells together in what's called a string. These 3 wired together are called a string of cells. They wire those strings together and they make a solar panel out of those strings of cells. And then they wire the solar panel to another solar panel, positive to negative, and you build your strings into modules, and you build your modules into solar arrays. Right? So you can try this with a bigger one if you want to see how much faster it will spin.
And how many of these do we have in our kit? Or are those not ours?
These are in your bigger kit. There's 4 of these in your larger kit.
Okay.
And now just another note here. What you're looking at here is...
Here, do you want me to hold the little one for you?
So this is shimmery solar. This is multi-crystalline solar. And here we have no shimmer. And this is what's known as monocrystal solar. And these are the kind of solar that's on the roof of your school. Now, a little interesting factoid about that. You'll notice that
you could hurt somebody.
Very, very fast. Yeah. So obviously, generating a good amount more power.
Whoa!
It doesn't take much.
Lift off.
Put that on your head.
Yeah.
But you'll notice that on the edges of these big ones I've given you, they're rounded. There's little cuts like on the edge of the solar cells.
Wow.
That's because when they made these single crystal cells, they actually just grew a big, giant, long crystal ingot. They grow them into about 3 feet long, and they're about 1 foot in diameter, and they're perfectly circular. If you just trace that little arch on the edge of these cells, you get a nice round crystal. And what they do then is they take that crystal and they cut it into very, very thin wafers that become your semiconductors or your solar cells here. And they actually then they cut the edges of those cells to make them square so that they can fit more cells in a smaller amount of surface area. So you can always tell people whether or not you're looking at a monocrystal or a multi-crystal cell. Monocrystal cells were made out of a singular crystal, and they're rounded at the edges. Where the multi-crystal cells, you can make this out of sand, out of broken window glass. You can make these out of anything, and they just pour that refined silicone into a form, and then they slice it. So it's always going to have square edges, and mono will always have rounded edges.
Are the mono ones more expensive?
It used to be that people thought monocrystal, or they were for a while, more efficient, but multi-crystal cells are now equally as efficient, and they cost about the same dollar per watt, about $3.25 to $3.50 a watt for power.
So why would the bigger ones? Why would our school go with the mono?
They probably just did it. But there could be a lot of reasons that they use those panels. That might be what the installer carries. That might have been, something they got a great deal on through a manufacturer. They could have been more locally produced. But generally, the panels all have 20-year warranties, and they all are generally producing about the same amount of efficiency from different companies. Now, that's with that kind of material. Now, here's a very different kind of solar material. This is called amorphous silicone. So you can see it's very flexible. I can bend the whole new solar. This is the same kind of solar that's in your calculators.
Oh.
But this is the future of solar energy because it's flexible, because it can withstand, the elements a little better, and because it's able to generate full light spectrum power. So.
And it'd be more resistant to breaking, right?
It is, and you don't need big aluminum bars to mount it onto your roof. You don't need to make holes in your roof. So they just put this kind of solar on the 9 schools in Portland, and they chose it because the roofs have so many vents and all kinds of things on them. And this solar, as you can see, when I connect this, and this starts spinning. If I cover one of these pieces of solar, the power is reduced, right? So there's shading issues with this because what we've done is we've wired these cells in a circuit, and if you break that circuit, you're going to reduce the amount of power that's available. And this is a big problem for solar arrays with the kind of technology you have. If they're not sited properly, and the sun comes around and say you have a flagpole or a tree, and that shade of that tree falls onto the solar